What if I told you that Meta may have just taught AI something it's never truly had before? The ability to trust its own reasoning. That's what's behind their new breakthrough called DeepComp, short for Deep Think with Confidence. And here's the wild headline. Using this system, an open-source model called GPT-OSS 120B scored a staggering 99.9% accuracy on the AIME 2025 math exam. A test so notoriously tough that even the best human students usually stumble on it. But the number alone isn't the real story. What makes this breakthrough special is how it was achieved. It's not about throwing more compute at the problem or building a trillion-parameter monster hidden behind closed doors. It's about something much more elegant. Teaching AI to recognize when it's confident, when it's uncertain, and how to act on that knowledge. This could mark a turning point in AI research, shifting the focus away from brute force and towards something that looks a lot more like intelligence. So let's dig into what DeepComp is, how it works, why it matters, and what it might mean for the future of reasoning AI. For years, the dominant way to improve reasoning in large language models has been what researchers call parallel thinking. Here's how it works. You take a hard problem, and instead of asking the model for just one answer, you ask it to generate dozens, hundreds, or even thousands of different solution paths. Then you let the majority vote decide. If that sounds a bit like crowdsourcing an exam, that's basically what it is. Imagine giving a riddle to 1,000 people and betting on whatever answer shows up the most. Odds are, you'll end up with the correct solution. And for a while, this approach pushed model accuracy forward. But here's the catch. Parallel thinking has two major flaws. The first is diminishing returns. Once you've scaled up to hundreds or thousands of solution paths, you don't actually get much better. In fact, sometimes you get worse, because all the low-quality reasoning starts polluting the vote. It's like asking a crowd of people for advice. At some point, the noise drowns out the signal. The second flaw is cost. Every extra reasoning path burns more tokens. More tokens mean more computation. More computation means more time and more money. At scale, this is brutal. Running massive models thousands of times per question isn't sustainable, even for companies with deep pockets. So while parallel thinking bought us progress, it wasn't a long-term solution. The field needed something smarter. This is where Meta's DeepComp comes in. Instead of treating every reasoning path as equal, it introduces a new dimension: confidence awareness. Think about solving a math problem yourself. You're moving step by step, everything's going fine, and then suddenly you hit a point where you're not sure. That feeling of uncertainty is a signal. You might be heading into a mistake. Humans use that signal all the time. We stop, reconsider, maybe backtrack. DeepComp gives AI a way to do the same thing. As the model works through a solution, it's not just spitting out tokens blindly. It's evaluating how confident it feels at each step. Strong confidence means keep going. Weak confidence means stop, or at least flag that path as unreliable. That's a simple idea on the surface, but in practice, it changes everything. Instead of brute force, you get something closer to surgical reasoning. The model spends less time wandering down dead ends and more time focusing on the paths that actually make sense. So how exactly does an AI measure its own confidence? This is where things get clever. At the smallest scale, there's something called token confidence. Every single symbol or word the model generates already has a probability behind it. A kind of built-in meter of how strongly the model believes in that choice. DeepComp doesn't just look at those probabilities in isolation. It averages them, checking for stability across multiple options. But tokens alone are noisy, so DeepComp zooms out. It uses something called group confidence, looking at bigger windows of tokens, smoothing over local spikes and dips. It's like zooming out from individual puzzle pieces to see how well whole sections of the puzzle fit together. Then there's tail confidence, which focuses on the final stretch of reasoning. Why? Because the end is where answers usually crystallize, and it's also where errors tend to sneak in. If the model is confident early but wobbly at the finish, that's a red flag. And finally, DeepComp checks the weakest links, the lowest confidence chunks of the entire reasoning trace. These fragile sections tell you where a solution is most likely to collapse. Taken together, these measures form what you can think of as a confidence profile for each solution path. Some paths look rock solid from start to finish. Others have shaky sections that undermine the whole thing. Now, instead of treating them all the same, the model can tell the difference. Of course, measuring confidence isn't enough on its own. The real power of DeepComp comes from how it uses those signals. In what Meta calls offline mode, the model generates multiple solutions and then filters out the weak ones after the fact. It's like grading a stack of essays and only keeping the ones that actually make sense. But the more radical shift is online mode. Here, the model monitors confidence as it goes. If it senses that confidence has dropped too low mid-solution, it can cut its losses and stop right there. Instead of wasting tokens finishing an answer that was doomed anyway, it just bails. This makes the model not just smarter, but faster and cheaper. And the results back it up. So what does this actually look like in practice? Let's go back to GPT-OSS 120B, the model Meta used for this benchmark. On the AIME 2025 exam, its baseline accuracy, just first try, no tricks, was 91.8%. With the traditional majority voting method, that crept up to 97%, not bad. But with DeepComp, the score shot up to 99.39%. That's essentially perfect. And here's the kicker, it achieved this while saving almost 85% of the tokens. This isn't just about one model either. DeepSeek 8B, a much smaller system, went from 83% to 93.3% accuracy using DeepComp, while slashing its token usage by 78%. Qwen 332B, another giant, leapt from 80.6% to 90.8% while using 56% fewer tokens. When you're operating near the ceiling of performance, these kinds of gains are extraordinary. You're not just inching forward, you're breaking through. And here's the part that really caught the attention of researchers. Implementing DeepComp is shockingly lightweight. You don't need to retrain the model from scratch. You don't need specialized data. You don't need to tweak endless hyperparameters. All it takes is adding confidence tracking, setting an early stop trigger, and passing thresholds through the API. Meta says you could pull this off in maybe 50 lines of code. That makes DeepComp a plug-and-play upgrade, not a massive engineering project. For companies trying to deploy AI at scale, that's a game changer. Now, let's not forget about the model itself. GPT-OSS 120B isn't just a generic large language model. It's been optimized specifically for math reasoning. Instead of feeding it a fire hose of random internet text, the researchers trained it using curriculum learning. That means it started with simple problems and worked its way up gradually to Olympiad-level challenges. Along the way, it wasn't just shown correct answers. It was also deliberately fed wrong ones, so it could learn how and why mistakes happen. On top of that, the team used specialized math data like textbooks, problem sets, and tailored attention mechanisms to handle reasoning more effectively. The result is a model built not just to recall formulas, but to actually reason through problems. To appreciate just how impressive 99.9% accuracy is, you need to understand the AIME exam itself. The test gives students 3 hours to solve just 15 problems. Every answer has to be a single integer between 0 and 999. There are no multiple choice options, no room for guessing. Each problem is designed to be a trap, forcing students to apply concepts in unexpected ways, to think laterally, to avoid common pitfalls. This is the exam that filters out strong math students from the truly exceptional, the ones bound for the International Math Olympiad. For an AI to essentially ace this test, it's not just solving equations. It's demonstrating reasoning ability on par with the world's best human minds. But there's another angle here that matters just as much as the performance. DeepComp and GPT-OSS 120B are open source. That's unusual. Most state-of-the-art reasoning techniques are locked up inside private labs. Think OpenAI, Anthropic, or Google. Meta's decision to open this up means anyone can examine the code, experiment with it, and build on top of it. Yes, that comes with risks. Misuse is a real concern. Bias and misinformation are always on the table. But the flip side is transparency. When more people can see how a system works, spot flaws, and propose fixes, the technology evolves faster and stays more honest. And it's already happening. Developers are porting DeepComp into local frameworks like llama.cpp, making it possible to run these techniques outside of big corporate environments. That's how democratization works. Not by keeping breakthroughs locked away, but by putting them into the hands of a global community. Another reason DeepComp feels so practical is its flexibility. You don't have to run it at maximum power all the time. If your priority is efficiency, you can run DeepComp low, which keeps only the most confident 10% of solution paths. That maximizes savings and still boosts accuracy. If your priority is accuracy, you can run DeepComp high, keeping 90% of solutions while still filtering out the weakest. In other words, you can tune it like a dial, depending on whether you care more about cost savings or squeezing out every last ounce of performance. That's not just clever engineering. That's something product teams can actually use. Stepping back, the bigger story here is what DeepComp represents. For years, progress in AI has meant scaling up. Bigger models, more data, more compute. And yes, that's taken us far. But scaling isn't infinite. Costs balloon. Performance plateaus. At some point, brute force alone stops being enough. DeepComp points toward a different path. Instead of throwing more at the problem, it shows that AI can get smarter by learning to evaluate itself, by trusting its own signals, by knowing when it's right, when it's wrong, and when to stop. That's not just optimization. That's a step toward real reasoning. And because it's open source, it's not just a meta advantage. It's a tool the entire AI community can build on. This could be the moment when the field pivots from a race about size to a race about strategy, from raw horsepower to intelligent self-regulation. So the question is, does DeepComp mark the beginning of a new era in reasoning AI, where models stop being brute force engines and start becoming self-aware problem solvers? Or is it just the opening shot in what could become a new arms race around confidence-driven intelligence? I'd love to hear your thoughts. Drop them in the comments. Hit like if this gave you something new to think about, and make sure you subscribe so you don't miss the next big leap in AI. Thanks for watching AI Ascension, and I'll see you in the next one.